do I have 45 minutes?
We have 45 minutes and then we have 15 minutes afterwards with the questions.
Sounds good.
Okay, so welcome everyone to this new edition of the Pore Lab lecture series. So today we have Behzad Ghanbarian from, now he is at Kansas, right?
Kansas
he has had a long stint in the US, started off in Wright State University where he took his PhD, and then he had a postdoc at University, or what's the name again? UTA, University of Texas, Austin. Yes. And now he has been hired as an assistant professor in Kansas, and he has also a group called Porous Media Research Lab. So that sounds almost like our name. So we're probably close in the research topics.
We're cousins.
Yeah. So I guess you're still trying to build up your group because you haven't had it for that long. So it's probably still up and growing. So today he will talk about single and two-phase rock typing. So please, Behzad, go ahead.
Well, thank you very much for the kind introduction. My name is Behzad Ghanbarian, assistant professor at Kansas State University. Some part of my research is rock typing. Some other part is solute transport and dispersion. So some of you probably know that I'm Persian. And talking about dispersion makes me feeling more comfortable because I feel like I'm talking about myself. But anyway, today I'm going to walk you through single and two-phase rock typing. First thing first, I'm going to have a brief introduction about rock typing, current models in the literature, and then I'm going to introduce you to two new approaches based on single and two-phase rock typing, and at the end I'm going to have summary and conclusion. So let's just start with the introduction part. What is rock typing actually? We people would like to classify things. When it comes to rocks, grouping rocks based on some similarities makes that rock typing actually. And as I mentioned, we human actually would like to classify things in different groups, like bad things versus good things, cat lovers versus dog lovers, men versus women, and so on and so forth. But when it comes to rocks and petroleum engineering, actually, we are interested in higher permeability rocks because they produce more oil and gas specifically. But how we can classify rocks, it's being done actually in different ways. If you talk to a geologist, they probably classify rocks based on similarities in mineralogy and mineralogical properties. If you talk to a petroleum engineer, it would be mainly based on hydraulic properties or petrophysical properties. And specifically, the way that it's being done in petroleum engineering, it's like we classify rocks based on similar characteristic pore sizes. And I'm going to tell you how it can be done. Several models have been proposed in petroleum engineering. Bruce, back in 1970, was among the very first who proposed rock typing, single phase rock typing. Winland has been actually widely applied for single phase rock typing. Lucia is the other one, hydraulic flow zone, or HU in briefly, reservoir quality index, and more specifically, very recently actually, a colleague and a friend of mine, Dr. Mizai, proposed true effective mobility function to classify rocks based on two-phase characteristics. So if you go back and check out the literature, there are so many different ways to classify rocks based on single-phase petrophysical properties, but there is a lack, still we have a lack to investigate how we can classify rocks based on two-phase characteristics like capillary pressure curve, water relative permeability, or mainly relative permeability curves. One of the empirical models that has been proposed before, it was developed by Dale Winland, who was working at Amoco back in years, and he didn't publish his results. He wrote a report, and his colleague Stanley Colucci actually mentioned his work. But based on Winland, he tried to make or establish a relationship between permeability, porosity, and R35, and that's his equation, empirical equation based on some sandstones, carbonate reservoir rocks, and also some other samples. So he had a pretty big database, mainly conventional rock, reservoir rocks. If you ask about R35, that's the pore throat size corresponding to the 35th percentile on the mercury intrusion capillary pressure, or MICP curve. K is permeability in millidarcies, and phi is porosity, fractional porosity. And as I said, Stanley Kolodzy, his colleague, actually published his results and also another sort of relationship, again, empirical equation to relate permeability, porosity to R35. And these are all results coming from Amoco that doesn't exist anymore. The company is gone, merged with some other companies. If you look at the literature, there are some other empirical relationships to connect some characteristic pore size to porosity, permeability. Pittman, back in 1992, proposed these empirical relationships, and you can definitely find other models. People try to propose different things. But Winland model has been widely used for rock typing purposes. The way it can be done is typically people plot permeability as a function of porosity, and then they plot different R35 values, and they classify rocks based on samples having very similar R35 values. This is one example from Moya et al. But the point is, Winland proposes a relationship mainly based on conventional reservoir rocks. These days, we are having unconventional tight gas sandstones, shales, mudstone, and so on and so forth being successfully explored and produced all around the world, not only in the United States. So you can actually see shale gas resources in different continents and so on. But the question is, people have been using Winland equation for rock typing purposes in tight gas sands. Here's one example. Here's the other example for unconventional reservoirs in Canada. But the question is Winland model really applicable to unconventional reservoir rocks, and more specifically, rock typing purposes? We wanted to answer that question. We got 18 tight gas sandstones from Texas, and we estimated permeability based on Winland equation. We plotted those estimations as a function of measured permeability. And as you can see, as expected, when you have an empirical relationship established based on conventional reservoir rocks, it's not gonna produce or results into accurate permeability predictions for unconventional reservoir rocks. More specifically, we found overestimation when we use Winland equation. Similar results were found by Rezai and his co-workers in a different study. So Winland model would overestimate permeability in unconventional reservoir rocks. That makes its application for rock typing purposes to unconventional reservoirs questionable. The other technique is hydraulic flow units, and that's based on modified Kozeny-Kármán equation. Amefield and his co-workers proposed a correlation between reservoir quality index, PHYSI, which is normalized porosity, and FCI. So what they do, they plot RQI as a function of PHYSI, and they try to find different FZI values. What is RQI? That can be actually calculated from the ratio of permeability to porosity. PHYSI can be calculated from porosity, and FZI has its own relationship. The point, here are some results based on hydraulic flow units. As soon as they find rock types, they can convert it back. They can convert back RQI and PHYSI to permeability and porosity easily using those equations that I just showed you. The point is, Kozeny-Kármán equation has restrictions. For example, it's not applicable to porous media with broad grain size distributions. It also won't be applicable to media whose grains and their shape is actually deviate strongly from a spherical shape and form. And also we know that Kosanik-Kármán equation is not going to work for media with high porosities like greater than 0.95, which is not the case when we talk about rocks, but there are limitations and restrictions when it comes to even modified Kosanik-Kármán equation. The other model that Zhu and Torres Redding proposed, it was based on Leverett reservoir quality index. So they typically have permeability versus porosity plotted, and they try to have different RQI values to classify rock types. So these are different techniques being proposed. And now I'm going to walk you through single phase rock typing based on a new approach that we developed back in 2019. One of the models based on theory, it was proposed back in 1986 by Johnson and his co-workers, and I'm going to use JKS for abbreviation. Permeability would be linked to formation factor or formation resistivity factor, and lambda. What is lambda? That's a characteristic pore size. So if you have lambda value and if you have formation factor, you can easily estimate permeability, and I'm going to tell you later how you can do that. But this is based on theory published back in Physical Review Letters in 1986. But the point is, what I have been showing you so far for rock typing purposes, people have permeability versus porosity, right? But you don't see porosity in this equation. The point is, if you merge the JKS model with any model like Archie's law and so on that connect information factor to porosity, you can actually find another relationship that relates permeability to porosity and the characteristic pore size. In this case, we were going to actually plot it up for some specific cases. We have lambda equals 1 micron and also lambda equals 10 microns. And it very much depends, the curves we get depends on the value of M. You probably know that as a rule of thumb, M would be equal to 2 if you don't have any idea what M is. And by the way, M is cementation exponent, typically set equal to 2. The point is, for different M values, we get different curves, although all these three curves belong to the same rock type because lambda is equal to 1 micron in both cases. So what I'm trying to show you here is if you have permeability porosity plot, you also need to have some sort of information about the cementation exponent because it matters when it comes to rock typing. There might be two rocks with the same characteristic pore size or lambda value, but because of the fact M values are different, they might show up in different rock types. Okay, so here is JKS model, including porosity and lambda. If you rewrite it, if you take the log of each side and rewrite it, actually you can get log of lambda in terms of log of C, log of K, and log of phi. And interestingly, this is very similar to other models proposed, like very similar to Winland equation. So by comparing these two equations, you get some theoretical insight about this constant coefficient or these empirical numerical prefactors in the Winland model. And that was one of the purposes of our study, to indicate that these are this simple theory actually can provide us some theoretical insight. And it also looks like Leverett reservoir quality index. Okay, to do single phase rock typing, we found 3 different databases, Sen et al. 1990, including 120 rock samples, the Katz and Thompson database, including 50 sandstones from eastern Utah mainly, and the last one includes 140 rock samples, clay-rich rock samples from different formations actually. And we're gonna use this form of permeability equation, JKS original function that relates permeability to formation factor and some characteristic pore size. Just to show you the variation in each database and also within different data sets that we found, you see permeability as a function of porosity, permeability as a function of reciprocal formation factor, and formation factor as a function of phi. For all the three databases, you get some sense. We are talking about different rock types and so on and so forth. Okay, for the first database, Sen et al. 1990, we mainly found 5 different rock types. And of course, you can actually define some other subcategories and subgroups. What we try to actually come up with the most reliable rock types we could. Interestingly, if you, and this is based on permeability versus reciprocal formation factor. So what we did in this case on the left graph, after plotting data, we came up with different lambda values who could describe those rocks and those samples, and we came up with some specific lambda values. Interestingly, when you plot the same rock samples within each group on a different plot, which is permeability as a function of porosity, they might belong to different, or they appear to belong to different rock types. For example, in this case, we have these blue dots actually over here. So they probably belong to R35 equals 0.17 microns. But these actually data points, or these data, might belong to a different rock types. And that's what we try to explain at the very beginning. By having permeability porosity plot, we may get uncertain rock types. This is result for Katz and Thompson database. We came up with 4 different rock types. Again, when you plot the data, the same rock types on the porosity permeability plot, they look pretty scattered, and there is a chance that they would be categorized in different groups and classes. For the Sen et al. Database 1988, we came up with 7 different groups. Again, same results. As you can see, red dots belong to the same rock type on K versus reciprocal formation factor. But when it comes to porosity permeability plot, they look actually pretty scattered. And someone may group this rock into another rock type and so on, so forth. So what we try to emphasize here is the impact of cementation exponent or formation factor is necessarily to be included when it comes to single phase rock typing. The question here is, do we think that the JKS model would be predictive? Is it capable of predicting permeability? So back in 1986, Johnson et al. Claimed that characteristic pore size, or lambda, can be related to the ratio of pore surface to pore volume. And if that ratio is known and measured, you can estimate lambda from that ratio and also the cementation exponent. Fortunately, for one of the 3 data sets we had, those data are available, and that's for Sen et al. 1988 databases, not for all 140 rock samples, but for 116 samples, those information were available. So we estimated permeability using the JKS model from SP to VP ratio, and also the formation, the cementation exponent, and we found underestimation. We explored that, why we are underestimating permeability, and when we plotted estimated lambda versus kind of like calculated lambda, we found that that relationship proposed by Johnson and his co-workers underestimate the value of lambda. So what is the other possibility? Can we use JKS model to accurately predict permeability? And the answer, short answer is yes. I'm gonna tell you how. Bonovar and Johnson a year later proposed another relationship to estimate lambda. And they said lambda would be linked to the pore diameter at the inflection point of the MICP. And there is a constant coefficient equal to 0.21. We use that relationship. We, for Katz and Thompson database, we have formation factor and the inflection point, and we found pretty good accurate permeability prediction over almost 6 orders of magnitude, as you can see. And we also explored if we are accurately estimating lambda. So calculated or estimated lambda versus calculated lambda over almost 3 orders of magnitude, we did a pretty good job on estimating lambda. Okay, so summary and conclusion for the first part, or single phase rock typing, we propose a theoretical relationship to connect permeability to formation factor and to find different classes of rocks. The relationship based on JKS model provided us some theoretical insight into the parameters of Winland's equation and some other empirical relationships proposed in the literature. Most of the rock types methods, actually, they ignore the impact of the cementation exponent or the formation factor, and we highlighted that in this study. And we also demonstrated that if you do rock typing based on permeability reciprocal formation factor, and you do rock typing and get some results, there is a chance that those rock types and samples belong to the same rock type on that plot. They may look actually scattered, and there is a chance that they belong or being classified into other rock types if you do that based on porosity permeability plot. There are also limitations in this approach for sure. We know that neither formation factor nor permeability being affected by contact angle and wettability properties of the system. So there is a chance that if there are 2 rock samples with the same characteristic pore size but different contact angles or different wettability properties, we classify them into the same rock type. That's one of the limitations we have. The other limitations is we know that most of petrophysical properties, petrophysical data, they would be stress dependent. If we want to get better and more representative rock types, we need to get permeability and formation factor measured under in situ conditions. We also know that formation factor, porosity, and permeability, these are all macroscopic quantities, right? They don't explain detailed microscopic characteristics of a rock. So if we have a rock sample showing multi-scale or multimodal behavior in its pore size distribution, because of the fact we are not including capillary pressure curve into our rock typing, there is a chance that it doesn't show up, and we come up with incorrect rock types. The other chance is we need core measurements for permeability and formation factor, and we know that these days most of petrophysical evaluations in reservoirs that are based on well log data, and core data are expensive and not always available. This is the paper we published back in 2019, all about single phase rock typing and so on, just in case you want to have a look later. Given that there are restrictions actually with single phase rock typing, we decided to expand what we proposed back in 2019. And we wanted to include the impact of wettability and also multi-scale, multimodal behavior, or in other words, microscopic properties of rocks. So we came up with 2-phase rock typing, which is going to use the same concept based on similarities in characteristic pore size. So the main idea is to classify rocks with similar characteristic pore sizes, but this time at different saturations. Previously, for single phase rock typing, we focused on full saturation. It could be liquid saturation equal to 1, gas saturation equal to 1, depending on you're measuring gas permeability or liquid permeability, but that was at full saturation. And this is the model we used, the JKS model. Interestingly, the JKS model is very similar to the critical path analysis model, which is another technique from statistical physics. Based on the CPA, or critical path analysis technique, permeability is related to critical pore radius to the second power. There's a constant coefficient C and also formation factor. So when you compare these two models, they are very similar in terms of mathematical form. That constant actually is going to be 72.2 divided by 4 if pore length is proportional to its radius. If they are independent, that constant coefficient would be 53.5 divided by 4. That characteristic or critical pore radius in the critical path analysis model, that RC can be estimated from the inflection point based on Katz and Thompson's article published back in 1986. So again, the main idea is to classify rocks based on similarities in pore sizes at different water saturations. For partial saturation, we can apply critical path analysis. Based on that, water permeability at SW, at some specific SW, would be proportional to RC. I should have used proportional sign rather than equal sign. Would be proportional to RC to some alpha. The value of alpha would be 3 within critical path analysis framework. If pore length is proportional to its radius, if they are independent, alpha would be 4. So if you take the ratio, water relative permeability would be a function of critical pore radius at full saturation and critical pore radius at partial saturation to some exponent, which is alpha. If you rewrite it, you can actually get that characteristic pore size. We call that within critical path analysis, we call that critical pore radius at some water saturation would be a function of RCSW at full saturation, KRW, which is water relative permeability, and the exponent alpha. In order to use that function, we need actually some other properties. We need RCSW equals 1. We also need water relative permeability or wetting phase relative permeability. We also need to know what the value of alpha is. Is it 3 or 4? And for rock typing purposes, we definitely need a large database, including different types of rocks. So we explored the literature, and let me tell you, before I get there, I need to tell you how we can estimate or determine RCSW equals 1 and so on and so forth. So for RCSW equals 1, it can be estimated based on Katz and Thompson's approach. It can be estimated from mercury intrusion porosity curve, or in other words, from the inflection point of the MICP curve. If you have pore throat size distribution, it can be estimated from the mode of pore throat size distribution. KRW is wetting phase or water relative permeability. It needs to be measured or simulated somehow. The value of alpha, which is either 3 or 4, can be determined from image analysis, or if you have permeability, formation factor, and MICP data, you can estimate what the value of alpha is. Is it 3 or 4? And I'm going to tell you more in details. So we explored the literature, and we couldn't find a large database including all these information like formation factor, permeability, MICP, and wetting phase relative permeability. So we decided to actually do our own pore network simulations. We considered so many different cases for pore size distribution. We use, by the way, we use the Martin Blunt's code that was developed by his PhD student Per Woldwatne back in 2004. So that code is based on Weibull distribution, and these are shape factors from Weibull distribution, delta and gamma. We use a pretty wide range of gamma from 1.35 to 24. We use 2 different things for pore shape distributions. Pore throat radius was actually ranged between 0.1 micron and 10 microns. For the other half of the simulations, it was between 1 and 100 microns. So you can easily see that we have 2 orders of magnitude change or variation in pore throat radius. For clay content, which is kind of like in charge of critical water saturation control, we use 2 different values. We use 3 different values for coordination numbers, 2, 4, 6. And you probably know that in most rocks, the average coordination number is around 4. We also wanted to include the effect of contact angle and wettability properties. So we use 2 different contact angles, 0 and 60. And overall, we came up with 240 simulations. So we have 240 different cases, 240 water relative permeability curves. Here is pore network 1. You can see pore body radius distribution here, pore throat length distribution here, pore throat radius distribution, and this is pore shape factor. Again, this is test 1 or pore network 1. This is pore network 49, 49 out of 240 actually. And you can see that, you know, we're covering a wide range of microscopic properties in terms of pore throats and pore bodies. Okay, so now I'm going to show you the results of pore network simulations. You see permeability versus porosity. These are all 240 simulations we have. Actually, permeability spans over 5 orders of magnitude. And we wanted to have porosity between 0.1 and 0.3, which is a typical range for rocks. And also formation factor, as you can see, it spans almost 2 orders of magnitude. Again, porosity has the same range. So we're kind of like covering a pretty wide range of rock types by means of pore network modeling. Here are the simulated water relative permeability curves. Again, we're covering a pretty wide range from kind of like pretty straight to pretty curvy water relative permeability data. This is natural scale. This is log scale. So we just wanted to show you how the tail would change at small water saturations. Just to walk you through the 2-phase rock typing. First thing first, we generated some synthetic pore networks by means of pore network simulations. We made sure that all the results are above the REV. So we had REV plots. We also simulated permeability, formation factor, water relative permeability. Capillary pressure curve was also simulated, but we didn't include that into our 2-phase rock typing because we have pore throat radius distribution. So what we needed to do next was kind of like figuring out which C value should be used. And that C value would tell us what alpha should be used, because at the end of the day, we're going to convert water relative permeability curves into critical pore radius curves. So based on the fact that we had simulated permeability, simulated formation factor, RC SW equals 1 can be estimated from the mode of the pore throat size distribution. So we have all these 3 quantities. We use C equals 72.2 divided by 4, and we also use the other value, and we double check which C value would result into more accurate permeability estimation. After doing that, we could figure out what alpha is, if it is 3 or 4, and using that alpha, we converted water relative permeability into critical pore radius out of these 2 relationships. And then what we did, we calculated the effective saturation, which is water saturation minus critical water saturation divided by 1 minus SWC. SWC was derived from the water relative permeability curve. And at the end, we plotted effective saturation as a function of that critical pore radius, because this is the characteristic pore size. And we wanted to show what's the, how it looks actually, and how characteristic pore size would change with effective saturation. And at the end, we classified rocks or pore networks based on this approach. All right, so here are the simulations from water relative permeability, again on log scale on the right and natural scale on the left. After we converted them, we found SE, which is effective saturation as a function of we are having a wrong label over here. This is RCSW divided by RCSW equals 1. We wanted that to be normalized between 0 and 1. So we kind of like scale that by dividing by its maximum. So these are converted plots, and we're going to use these plots to classify rocks. To do so, we use the curve clustering approach proposed by Gaffney in his PhD dissertation back in 2004. And we came up with 12 different rock types. Again, what you see is effective saturation versus scaled critical pore radius. Again, wrong labels here. They have to be divided by RCSW equals 1 to be ranged between 0 and 1. And based on this curve clustering approach, we classify them into 12 different cases. Interestingly, when you plot permeability versus porosity for different rock types, we can easily see that these pore networks, although they belong to the same rock type based on water relative permeability or two-phase rock typing, when it comes to single-phase data and by plotting permeability versus porosity, obviously they belong to different rock types. You know, you can actually have a curve going through all these pore networks and another curve going through these bunch of data points and two other curves from going through the other cases for rock type 1, but they look pretty scattered. And we did the same thing for permeability versus reciprocal formation factor. In most cases, within a specific rock type, we see pretty scattered data and we see different slopes. In this case, for example, here is one, if you do single phase rock typing, here is one rock type and here is the other rock type. You can easily see the same pattern here in this rock type 2 and over here as well, which means if you do two-phase rock typing, which includes the effect of multi-scale behavior in macroscopic quantities and also wettability or contact angle, you get different results than single-phase rock typing. So by providing more information and more detailed characteristics of your pore networks or your rock samples, you would come up with different results and probably more accurate rock types at the end of the day. Again, as a summary and conclusion, we propose a theoretical based framework for two-phase rock typing, which includes the impact of bimodality and multimodality in pore size distribution, and also the contact angle. The results we get out of this two-phase rock typing, they're not necessarily the same as the results we can get out of single-phase rock typing. For example, if you do two-phase rock typing, there might be some rocks or pore networks belonging to the same type, but if you plot the same pore networks on permeability reciprocal formation factor or porosity permeability plots, they may look scattered. And the obtained results actually highlights the importance of two-phase rock typing. And as I mentioned before, by focusing on single-phase data, we're going to ignore the impact of wettability, contact angle, and also some other detailed information about microscopic properties in a medium. At the end, I would like to appreciate my two colleagues and mentors and fellows, Dr. Larry Legg from UT Austin, that I had the honor to work with him, Dr. Mohammed Sahimi from USC, that also, it was a great pleasure to work with him on this project, specifically two-phase rock typing, and also my graduate student, Brandon Euclid, who has been working on this two-phase rock typing in the past 2 years. And at the end, if you have any question, I will be more than happy to answer those questions.
So then we're open for questions from the audience. Please just unmute if you have any questions. If there are not anyone from the audience, I can start off. I didn't really catch when you generated all those pore networks and generated all the Relperm curves. What was the spread in wettability you added to the models?
So we used two different contact angles. We couldn't actually go far beyond two different values. Right now, we have 240 simulations, and each simulation was actually iterated 100 times. So you can easily see that they are computationally really demanding. So if we wanted to include like more contact angle values, that would be possible, but it required more time and more computations that we decided to cut at two different 0 and 60 degrees. But definitely if you include more, there is a chance that you get different results.
Follow up on that. When you plotted the formation factors versus porosity, I guess it seemed like you had already quite some strong trends there. Could you explain why you're getting those trends? I guess it's some constants in the network generation that is not spreading out the room.
Well, I asked my graduate student Brandon to start fitting Archie's law and see what kind of a cementation exponent we get. We haven't done that yet, but that's exactly what we wondered, why there is some sort of similar slopes actually in data. They're not exactly the same, but very similar cementation exponent. We don't know what exactly the M values are, but that's the thing that we're going to explore actually in the following weeks after my student is back from holiday season. But good point, yeah. Good catch actually.
But it's not like you have one parameter in the network generation which just have very specific values which are not picked randomly, or?
So I don't think so, because if you look at, for example, I don't know what the gamma values are in these two cases, but one has a pretty narrow pore throat radius distribution. The other one has a pretty broad. One is left skewed, the other one is right skewed. So we're kind of like covering a pretty different range of porous rocks. But one possibility is formation factor is not affected by microscopic properties as much as permeability does. So although we have a pretty wide range and pretty scattered plot on the left, it doesn't look like scattered as much as it does on the formation factor, because formation factor is not impacted by microscopic properties as the permeability does.
Yes. But do you think that those trends you see in the formation factor versus porosity are some of the same rock types you're picking up in the two-phase rock typing later on?
Okay, good point. The way that rock typing has been done in the literature is based on finding rocks with similar characteristic pore size rather than similar formation factors or similar cementation exponents. And that's because of the fact the main contributors to permeability, because we are doing rock typing because permeability matters to us. We wanna know which rock type is more permeable, which rock type is less permeable, because the more permeable one is gonna produce more oil and gas for us, right? The main contributor to permeability is characteristic pore size rather than formation factor. Formation factor, permeability is not sensitive to formation factor as much as it does, and it would be more sensitive to characteristic pore size. So the main contributor is characteristic pore size when it comes to rock typing, and formation factor would be kind of like has a lower impact on permeability and rock typing.
Thank you. Any other questions from the audience?
I got.
Go ahead, Mehdi.
I got a question. Hi, Behzad. My question is, how did you simulate the effect of cementation actually in your simulation? Do you consider different cementing or?
Oh, okay, good question, Mehdi. Thanks for bringing that up. No, within pore network simulations, we didn't impact any diagenesis or cementation or anything like that. We don't have that ability or capability within Martin Blount's code, not as much as I know about the code. So we didn't include any cementation. Mainly, we get different M values probably because of the heterogeneity in pore throat size distribution. That's at least what I think. But we didn't include any trapping. We didn't include any cementation. So these are probably pretty straightforward water relative permeability simulations.
My next question is, how did you validate your findings actually? And because I didn't see any validation. So, okay, you have done some kind of simulation. In the end, you say the data is not scattered, so it looks nice. So it shows that the equation works.
Okay.
Is it?
Good point. Two things. First, we use the same code for 4 Fontainebleau sandstones from Lindquist et al. And we match their water relative permeability with the simulated water relative permeability based on lattice-Boltzmann simulations and what Chris Arns and his co-workers did back in 2004. So that was some part of validation. The other thing is Dr. Mirzai, my colleague, actually provided us some experimental data, and we have capillary pressure curve and relative permeability curves. We're gonna evaluate this two-phase rock typing using experimental data, and that's what we haven't done that yet, but that's on the horizon to be done, hopefully after holiday season.
All right, thank you. That's all from me.
Thank you, Mehdi.
And we have one question on the chat now. Hi, Behzad, great, I guess it means a great talk or something. Our question, why wetting phase KR has been used for two-phase rock typing?
Right, good point. That's my colleague and friend Abu Zar. So based on critical path analysis, by means of critical path analysis, you would be able to only model the wetting phase. Critical path analysis doesn't provide you any theoretical way to model non-wetting phase. So that's the reason, the main reason we stick to water relative permeability, because critical path analysis won't provide us any theoretical relationship between critical pore radius and permeability.
Any other questions from the audience? If not, then I think we thank you, Behzad, for a great talk. It was interesting.
Well, thanks for having me today. It was great pleasure to be actually with you today, and other colleagues and other friends around you.
Hopefully we'll meet in flesh soon when the vaccine is coming and everything will be good again. Okay, thanks you. Thank you.
All right. Thank you, everybody.
Bye.